Final scalability and consensus speaker is IBM researcher Marko Vukolic.
Thank you. So I will be giving actually a premiere talk on the recent work that we did in IBM Research Zurich. It's with my colleagues Chris Statakopoulos and Tudor David. It's about high throughput BFT for blockchains. Essentially, so it's a fairly technical talk, but I will do level setting hopefully properly so we can all follow. And let's start from the beginning. So what is a blockchain for the purpose of this talk? So it's really a total order of blocks, so a chain or sequence of blocks, and each block contains a totally ordered list of transactions. So we are not considering here execution or anything. So we are just considering like how to reach this total order on this data structure. So of course, if you have this data structure on a single laptop, you don't have a blockchain. So essentially what blockchains do, they replicate this data structure across a network of mutually untrusted nodes. So essentially there is some adversarial setting, and basically we want consensus protocol. And consensus protocol is those that keep this data structure in sync. And basically consensus research is about making these protocols secure, correct, and efficient in the end. So this is the context. So we are not considering smart contract execution. When I talk about performance, it's basically how fast can we order these transactions on a blockchain. A bit of level setting further, I will be talking about Byzantine fault model. So this is a model where you have let's assume fixed for the purpose of the talk, but it can be like this number of nodes can vary. And up to 1/3 of them can be malicious. The network can behave adversarially, it can drop messages, reorder them, delay them. But we assume that from time to time, network is synchronous, like it allows us basically some progress in this sense. So typically in literature, this is modeled by some global stabilization time that's unknown to nodes, after which the network is synchronous. But what it really means is that only periodically the network is synchronous. Otherwise, we really don't rely on correctness of the protocol, especially safety, on synchrony assumptions. And the problem with which model consensus is we reduce to total order broadcast, because we want these transactions to be totally ordered across nodes. Essentially, we will model consensus as total order broadcast. So total order broadcast has 4 properties. So agreement, which says that all correct nodes at a given position agree on the same transaction. Validity, that only correctly proposed, if you want, by authorized client transactions are added to the ledger. No duplication means that there will be no duplication of a submitted transaction to the blockchain. And liveness, basically that every transaction that a correct client submits to a blockchain is essentially added to the blockchain at some point. So this is the problem I'm considering. So what I will be talking about is essentially what's the highest throughput consensus or total order protocol to date on wide area networks, certainly with up to 100 nodes and probably more. We just didn't test it yet to that scale. This is not like, this doesn't leverage any side chains or whatever, so I'm really talking about a single chain of blocks. So this is your layer 1 solution if you want. This protocol is suitable obviously for permission blockchain. It was initially designed for Hyperledger Fabric, and it's going to be implemented in Hyperledger Fabric. I'm going to discuss it. But also for proof-of-stake permissionless blockchains, and I will give more context about this. So it's relevant for permission and permissionless blockchain at the same time. So a bit of the history of consensus for blockchain is, of course, started with Bitcoin's proof of work, but then with the issues that we all know here about, so like very high energy consumption, right? Finality, because it's a probabilistic protocol, we can switch from fork to fork, which can be annoying, right? And basically what this line of research that Mir BFT, the protocol I'm presenting, falls into is about improving the very poor performance of proof of work. And essentially, Bitcoin proof of work will give you 7 transactions per second. With some tweaks to proof of work, you can get probably an order of magnitude more, but not more than that, so like 60, 70. And it has very high latency, right? So blocks are produced every 10 minutes. With 6-block confirmation, you have your latency of 1 hour. So essentially where a lot of blockchains goes, especially permission blockchain and proof-of-stake permissionless blockchains, that use this BFT in the model I just introduced. And essentially they leverage protocols such as PBFT, you may have heard of, Tendermint, BFT Smart, Algorand, Honeybadger, and many, many others, to essentially solve these issues that we have with Bitcoin-style proof of work. And Mir BFT falls into this category of protocols, if you will. So briefly, how the situation looks like. So if we have few aspects of consensus protocols for blockchains, here scalability, fairness, energy sustainability, consensus finality, and performance. I will introduce a bit more fairness. Essentially, the situation proof of work looks like this. So it's kind of scalable, but the performance is bad. There is always a trade-off between these two things. But it's fair in a sense that any node that joins the blockchain network has basically probability which is not equal, but is depending on the computing power. But in a sense, given the same computing power, the probability is equal to produce the blocks. Byzantine fault tolerance traditionally comes from the database replication world. And as you see, it has addresses many issues that proof of work blockchain consensus has. And I put the performance in yellow. I don't know if you can see it from the chairs, but the performance is in yellow, so it's considerably better than proof of work, but it's still not there, as you will see. For fairness, we'll see some issues, right? So there are some protocols that try to essentially modify the protocols, BFT protocols that come from the database replication world to blockchain that address fairness, but in principle, fairness and scalability are issues. And mere BFT, well, not surprisingly, they will go green in all the aspects. It's also, we can discuss some aspects. So scalability, obviously, I position myself into 100 nodes. You can claim that this is not scalable, but basically, this is not the limit of mere BFT. And it scales pretty well, as you will see. So let's go into a bit of more details. To understand how we designed mere, you need to understand take the classical BFT protocol and understand its bottlenecks. So this is what I'm doing on this slide. So when you want to tolerate one Byzantine fault, your F is 1, and your minimum number of nodes is 4. This is why I have 4 nodes on the slide. And basically, the protocol, such as PBFT that I'm describing here. So PBFT is the classical, most scrutinized protocol in the literature, 20 years old. That's basically the basis for all this BFT-based blockchain consensus protocol out there. So this is why I'm actually describing it and its bottlenecks. So essentially, we have the primary that aggregates transactions in a batch. So it forms a batch, which is a predecessor of a block. Sometimes it's the block itself, and essentially distributes this block to all nodes. So it's open connections to all nodes and sends the block to all nodes. Then, because the leader, of course, the primary can be malicious, these nodes will have an all-to-all round of exchange of information basically of the hash of the information that the primary sent. And for some reason that I don't have time to talk about, they need to do it once more, but not for the 4th time. So basically, the whole pattern of the protocol looks like that. But if majority, and here we talk about 2/3 majority of nodes agree basically on the block that the leader sent, we can now deliver the block and add it to the blockchain. So this is where the protocol in common case ends. Where are the bottlenecks of this protocol, right? So people are tended to assume that it's in the n-square communication phase. But n-square communication phase is actually, as I mentioned, so it's an exchange, so basically on the hash of the block of the batch that the leader sent. So the nodes are agreeing on this. So these are actually very small messages. They're also load balanced across n replicas, n nodes. So essentially, this is not the bottleneck. What's actually the bottleneck in this protocol is the first phase, where the leader uses its basically bandwidth to disseminate the protocol to all nodes. And essentially, this is the reason that PBFT as a protocol doesn't scale well. So you see here, I plotted with the number of replicas. This is an easy calculation. The more replicas you need to replicate the block to, essentially the more work network-wise leader has to do, and your throughput, which is plotted with respect to number of replicas, theoretical peak throughput of a protocol such as PBFT is basically inversely proportional to the number of nodes. So it doesn't scale well. So we are going to, in mere BFT design, we are going to attack this. So how we came to mere BFT design? So there are several ways you can improve the throughput of PBFT. On very fast networks, for example, on local area networks, these are not very relevant for blockchains. Sometimes there are, right? For example, in permissioned deployments. But let's just bear with me here. We can use the pipelining. So basically, the leader can send multiple blocks in parallel. So that helps us in a sense that, like, if the latency doesn't dominate the throughput, right? So the leader, as soon as it sends the block to all, it can start with another block, but it doesn't help us with the network bottleneck, which is on wide area network present of the leader. So another idea how to address this and to add more fairness to this protocol is essentially what in research literature there is a protocol called spinning, 10 years old, and the idea is taken by Tendermint for you that come from the industry, blockchain industry world. So essentially the idea is that to let this one leader finish ordering one block, and then another leader will take over and propose another block. So this is fine for fairness, but it doesn't help us. So the bottleneck of replicating the data to all the nodes stays there, so Tendermint addresses there by introducing gossip. But essentially what happens is that the latency dictates how many blocks in flight can you have at a time. And if this your 3-message delay latencies across wide area network, this roughly means that you can have 2 blocks flying at the network at any given second max. Because that 3-phase delay latency is not going to be less than 500 milliseconds, like most of the time. So that's, we are getting there with respect to fairness, but we are not there, right? There is another idea, and this was Mir at some point of its design, right? So we wanted to combine PBFT pipelining with like spinning and Tendermint ideas, but we wanted to rotate the leader as soon as it gets the block from the first leader. So this was fine, and the performance was not bad, but it was still not there. Essentially, the number of blocks that you can propose depends on the path that you can establish across replicas, right? So there is essentially a chain of latency chain between the replicas, and it dictates inversely proportionally to this. It dictates how many blocks can you have in flight. And then finally, we realized, well, I don't know if you see this, but I will have another, like from these chairs. But we are going to just let all the nodes, in the best case where all the nodes are the leaders, to propose blocks in parallel. So they will have deterministically partitioned block space number, block sequence number space. So for example, in this figure that I don't know if you can see from the chairs, like node 0 has responsibility for all transactions which are modulo 1, which have the modulus 1 when divided by 4, and the second node has 2, essentially. The third node has 3, and the final node has modulo 0, right? So this is the idea. Of course, we will see some challenges with this fairly simple idea. So where Mir BFT is based is that we have multiple leaders in parallel. So this is the main idea. So instead of PBFT single leader, we'll have multiple leaders propose requests in parallel. But not only that, right? So it turns out that you need a highly parallelized implementation. So our implementation not only does it like severely multi-threaded, like it has many threads that are essentially responsible for running this protocol. Essentially, for each and every block that is ordered by a single leader, we have one thread that's responsible only for that. So essentially, it's like you have the PBFT instance per each of these blocks. But not only that, but the networking is also parallelized. So essentially, we don't use the single TCP, TLS, whatever is your preferred connectivity connection between every pair of nodes, but you use multiple ones. Essentially, you're losing the ordering, like the ordering between these streams, but it's okay because we can handle it, right? The key of actually using multiple leaders in a meaningful sense, such that the protocol is robust to malicious attack, is to prevent request duplication. And I will dive into this in a bit more details. So we prevent request duplication by essentially using rotating assignment of partition hash space across leaders. And I will spend some time on this because this is a key concept in Mir BFT to try to make sure that you understand it. Now, this is probably the most critical feature of Mir BFT and one that we are very proud of. So you can call it an incremental protocol. So it's not a new BFT protocol, strictly speaking, but actually, so it has configuration parameter where it's actually PBFT. It has another configuration parameter where it looks like Tendermint. But like you can tweak these configuration parameters to get Mir BFT protocol with immensely high throughput. Why is this important? It's extremely important for correctness. Like as I said, this PBFT protocol is out there for 20 years. So we have PhD theses that verify the correctness of the protocol, like in IO automata, formal verification, etc. So you don't want to lose this. And essentially, safety-wise, Mere BFT is exactly the same as PBFT. Where it differs is in the liveness part and how it handles multiple leaders. So basically, the changes that we introduce are only with respect to PBFT leader election part. And we have few optimizations that now you probably cannot see, but these improve the performance a bit more. So essentially, for some blockchains, it's not required that you deliver the transactions to all the nodes. So we basically have some sharding of to which nodes we deliver a transaction. And we have signature sharding. So essentially, we are not cheating. So in vanilla version of Mir, every replica validates signatures for authenticity of a client's request. It validates the digital signature of a client. Basically, you need to validate these signatures only to be sure that at least one correct node validates this signature. So you can basically reduce, by signature sharding, you can reduce, not verify this signature at 3 f+1 nodes, but at f+1 nodes. And as such, you're sure that one correct replica validated the signature. So these are optimizations, but I'm not going to focus much on them. So here you have, I'm not sure I should expect you to read this, but there is how we transition from PBFT to Mir. So for those of you who are familiar with PBFT, essentially it progresses in a sequence of views. And in each such view, the primary that I described is the leader. It's responsible for proposing the blocks, and it stays the leader until there is a fault. So essentially, this is the point where PBFT is not fair. So if you let the protocol run, it will just run with a single leader proposing the blocks, right? So this is where Tendermint, for example, jumps in and rotates the leaders, etc. So here, per round leaders, so we do have one view primary and epoch primary. So this is the node that actually takes us to the epoch. But within an epoch, we have many leaders. And depending on an epoch, which corresponds to a view in PBFT, we can have from anywhere from N1 to N leaders. How do we select the leaders? Well, in PBFT, obviously, primary is the only leader, so this is how we select it. And in Mir BFT, we go with a simple design in this implementation that we have, is which the primary simply announces the set of leaders it believes they should be leading the protocol. There are some limitations of this, like the primary cannot switch to one leader only or go to full set of leaders. So there are some rules which need to be validated by other nodes when the primary proposes a set of epoch leaders. And essentially, the other features are more or less the same. So essentially, Mir BFT really mimics PBFT. So whenever this one leader, one of the multiple leaders proposes a block, the protocol proceeds exactly like PBFT. OK, so how does it work without faulty replicas? So in what we call stable epoch, you can define a stable epoch with respect to the number of leaders in a protocol. So in this talk and in the paper that I will point you at the end of the talk, leader set is defined, so maximum leader set is defined as all replicas. So we are going to, whenever possible, increase the leader set. If we have less than n leaders, we are going towards n leaders. This doesn't have to be the case. But we want to achieve maximum throughput, and actually this, maybe surprisingly, but this works up to 100 nodes pretty well. Sequence numbers are initially partitioned among replicas. So whenever you enter an epoch, you as a leader, you know which block you're supposed to propose, essentially for which block you are the leader. And we stay in the same epoch, if it's a stable epoch, until there are faults. And then we have something that's called ungracious epoch change protocol. I will discuss it briefly. So how does it work? The main challenge with multiple leaders is, of course, request duplication. So there are some protocols out there, I won't go into naming the protocols, that have the similar idea. So you try to leverage the bandwidth available by actually having multiple leaders, but essentially there is a problem that a client might send a transaction to multiple nodes, and this transaction might appear in the blockchain several times. So graphically, this client sends a transaction to 2 nodes, and now because they all propose blocks in parallel, they simply add, node 0 adds the transaction in a block, and node 1 adds the transaction in a block, right? And basically, as they go, it might be especially in our implementation, right, that goes in parallel, you wouldn't detect this, but this is in general an issue. So you're ordering you have a blockchain which essentially repeats the transactions. Now, we have the total order. So essentially, what blockchains that allow this will do, consensus protocol that allows this will do, they will filter out duplicates after ordering. And that's fine, because you know exactly which of the duplicates is like first and which is the second, because you have total order, and you can filter this out. But, I mean, it's not helping us. Like, obviously, you can imagine this situation where the client replicates to n nodes, and essentially you have the n-fold duplication of each and every transaction. So in the end, our throughput would look exactly the same like PBFT. It would go inversely proportional to the number of nodes, so we need to handle inside the protocol this. And this is the key novelty, if you want, of mere BFT. So how do we, so essentially mere BFT prevents this. How do we do it? We do it with variant of consistent hashing. So we are going to have essentially consistent hashing or transaction sharding, so at each given point in time, there will be only a single leader responsible for a given transaction. So it's like you use a collision-free. You'll see, if I have time, I can discuss why you need a collision-free hash function to partition transactions in buckets. So each leader is responsible at any given time for a unique bucket and can propose only transactions that belong to this bucket. This is called an active bucket for the leader. But of course, I mean, because of the censorship, so nodes can be Byzantine, right? So if you send your transactions to me, I might be motivated to include them in the blockchain. For example, if you give me transaction fees, which we are abstracting out from here. So this protocol, you can apply it in networks that do have cryptocurrency and don't have cryptocurrency. So we are not relying on incentives to basically decide whether to include a transaction or not. But you send me a transaction, I don't like it, I just drop it to the floor. And because I'm the only one who can propose it, like this won't work. So this is why we actually have the rotating, this assignment of buckets rotates in time. And this is the key idea. So graphically, I have 4 nodes and 4 buckets here. And I have the transaction number 12, which hashes to the first quarter of the hash space. And as such, it's assigned to node number 0 or 1, so the top node there. And the other transaction 13, it hashes to the third quarter of the hash space, and as such, it should be proposed. So the active bucket belongs to node, let's call them 1, 2, 3, 4, to node 3. And that's it. So there will be no request duplication at given point in time, because only one node is allowed to propose this transaction. But if a node fails, we have the rotating deterministically. It works deterministically, right? Deterministically every so many blocks, and this is a configuration parameter, obviously. There is nothing hard-coded here. There is a configuration parameter that says how often you rotate. And if you rotate, well, what will happen is that the active buckets that are shown in bold will rotate, and the bucket, the transaction number 13 that falls into the third bucket will be assigned to the fourth node, which will then propose the transaction. So this is the key, if you want, mechanism that's like nothing spectacularly new, but this use of consistent hashing is new in the context of BFT protocols that helps mere BFT achieve the throughput that I was hinting at, and that you will see very soon how much it is. How do leaders set grow and shrink? So I won't have time for the details. See the paper. I'm including the link, and it's easy to Google for the paper. In principle, with a stable epoch, when you reach the desired number of leaders, you stay there until there is a fault. If there is a fault, you need to go to recovery epoch. And in recovery epoch, essentially the number of leaders is smaller than this threshold stable leaders. And when we transition from stable epoch to recovery epoch, or any epoch transition that's caused by faults or partition, we are talking about ungracious epoch change. For those of you familiar with PBFT protocol, this really corresponds to view change in PBFT. So in that case, the leader set must shrink. So if it was n, it needs to, you can have your configuration parameters, but it needs to be at least n-1. It can be n-half. This is tunable. So we use n-1 in our experiments. Gracious epoch change is when the recovery epoch ends, and the recovery epoch is defined as the one that has the number of leaders smaller than your desired number of leaders. When that happens, we transition to the next epoch, and the number of leaders is not allowed to reduce, but to prevent churns in case of some nodes that are actually down for maintenance or whatever. It only grows if the epoch primary thinks it should grow. But I will stop there, right? So this is also one of the elaborate parts of the protocol. But essentially, if you have faults, leader set shrinks. If you don't have faults and everything behaves nicely, but you don't have your n leaders, the leader set will grow. OK, so we come to the point like why this protocol is interesting, right? So we did elaborate, like we have a POC that's beyond POC, so it's a pretty elaborate implementation of the protocol. With the best case, also worst case, there are only a few things missing to call it production ready. So what are the baselines? So the baselines for performance evaluation comparison are PBFT, which leverages our code base. So we just tune Mir to simulate, if you want, PBFT with a single leader at a time, but otherwise it's our code base because we want fair comparison. We are comparing to best path chain. So this protocol exists as a consensus protocol, but it's not used in blockchain because the pattern you see there. So it's like there is a leader, it sends a block only to one node, and that leader, when it gets the block, forms another block, it sends it to another node. So that is extremely efficient protocol. It's not really robust because like any node breaking this chain, you need to reconfigure, essentially. So there are schemes and mechanisms in which you fall back from this protocol to PBFT to have robustness. But essentially, we are just comparing to really optimistic case of chain. Not only that, but we are doing chain in the best path. So if nodes are distributed across wide area, we will manually select for chain like really the best path throughput-wise and latency-wise that it can take so it can compare to Mir. We did elaborate evaluation on wide area networks with using 16 data centers on IBM Cloud. Machines are fairly beefy, so they're 32 vCPU, 32 gigs of RAM VMs. Notice that they do heavy, like the throughput will be fairly high. So all this transaction needs to be at least for each and every transaction without the signature sharding optimization. You need to validate digital signature for each and every transaction and each and every node. We did 1 gigabit, we took 1 gigabit network, so obviously the bandwidth of the network matters here. So we took a 1 gigabit network. It's not, it may seem much, but for like enterprise networks, this is not much even on wide area. We went up to 100 nodes, and the workload has 500 byte transactions to essentially mimic Bitcoin average size transactions. And large transactions, which are 3.5 kilobytes, which are Hyperledger Fabric average size because they contain 2x599 certificates. Let's stop there. So they're just large transactions. And we have some evaluation on local area networks that I'm not showing here because it's less interesting. We also compared to Honey Badger BFT. I'm not showing it here because it performs worse than our version of PBFT for all, for basically all data points that we took. So I'm not showing it here on the slide. So how does it perform? So this is one wide area network performance for Hyperledger Fabric size transactions for 3.5 thousand bytes transactions. What is our goal? So why we actually started doing this? So the legend is down, and this red line, if you can see it, dashed red line is the Fabric validation bottleneck. For those of you who are familiar with Hyperledger Fabric, it has the execute order validate architecture, and the validation can process 4.5 thousand transactions with that basically CPU that we are using in the setup. It can process 4,500 transactions per second. So if you don't want to make the consensus the bottleneck of the system, what you want is a consensus protocol that's above this line. PBFT scales like this. And this is not surprising, right? So we discussed how it theoretically scales. Well, in practice, it scales just like that. So it will be above the, for example, it will be useful for us in Fabric without creating bottlenecks, only for a very small number of nodes. You see, this is like 10 nodes and less. Chain scales really nicely, right? Especially if you give this manual path. But remember, this is not a real protocol. This is only an optimistic protocol. It's still below, so it's like in this experiment, it goes up to 4,000 transactions per second, and it's still below the line. Now, the nice part about this talk and the nicest moment of this talk is there is a lot of white space above the line. And essentially, Mir scales like this. So the scalability, if you want a flat line, is not ideal, and we are working on that, but the results are impressive. I deem them impressive. I don't know if you like them. So let's dive into the results. So with 100 nodes, with 100 leaders at the same time, So maybe contrary to the intuition. The protocol would order more than 8,300 transactions per second. If you go to the smaller scales, like at 50 nodes, remember that the EOS blockchain uses 20 validators. Your Cosmos network is 100 validators. So this is like where it compares to. And for very small networks, like for very small Hyperledger Fabric deployments, you might have 4 nodes. And then you have the blazing 20,000 transactions per second. This is on wide area. On local area network, it of course goes higher, but I'm not showing this. Some of you here certainly don't care about Hyperledger Fabric, so how the thing performs with Bitcoin transaction sizes, right? So let's see that. And that's then relevant for more for blockchains that will use proof of stake to replace Bitcoin proof of work, etc. So how does it look like? Well, PBFT scales again poorly. The performance is extremely good at low number of nodes, right? This is mostly because of this parallel networking that we have. So this, as a byproduct, we have a PBFT implementation that's like the best to date. Because you use parallel networking. Whenever you open a wide area network connection, your bandwidth delay product will harm your maximum throughput that you achieve. You just run the net perf between two VMs on separate data centers. But if you open another net perf, well, basically it's not divided, like the throughput on each connection is not divided by 2. It just goes up, the aggregate throughput. So this is the trick that happens here. Chain scales again nicely, and it tops at 20,000 Bitcoin transactions per second. And Mir would go like this. So this is why the claims stop at 100 nodes. But again, if you disregard chain as not really the robust BFT protocol, the gap between state of the art, and remember Honey Badger would sit below PBFT on this plot, is actually really high. So on 100 nodes, we are ordering more than 23,000 transactions per second with this protocol. And remember, this is only 1 gigabit connectivity. Okay, there is one slide repeated. But what is the impact of optimizations? I said there are some optimizations, and essentially I will finish soon. So I'm a bit over time, but I will finish very soon. What is the impact of optimization? So if we rotate the buckets, you see the difference. So the vanilla Mir with bucket rotation on 16 data centers goes to 15,000 transactions per second, and in the idealized non-robust version, without bucket rotation, you have 80,000 transactions per second. So the penalty that you pay for bucket rotation is not actually that high. It is 20%, but we stay a lot higher than the baselines. So the last, I want to talk about latency because it's important. Just quickly, so these are the latency throughput plots. So you should read against the y-axis here, and the typical latencies are about 1 second on wide area. This plot shows the experiment with faults, which we also did, but I will skip it for the sake of time. So it's important just to see that when we grow the number of leaders, which is the part of the figure when we go from 14 to 15 to 16 leaders, the performance doesn't drop. The paper is available. You can find it on the web. The protocol is supposed to be and is going to be implemented in Hyperledger Fabric, but as a standalone library, this is the goal. And that's it. Thank you very much.